Hello folks, it's Professor Fiore, and now we're going to take a look at distortion measurement using Tina TI. We'll begin with a very simple common emitter amplifier, non-swamped, decent sized input signal over here, 20 millivolts peak, which is going to get us a couple of volts out of here. I'm not really concerned about doing the analysis for this amplifier so much as I am just to see how we can quantify the amount of distortion. And the way we typically do that is through a parameter called THD, which stands for total harmonic distortion. So first, let's take a look at the output of the amplifier in the time domain. So I'm just going to do a straight transient plot here, see what we get. All right, so our input signal, our little 20 millivolt peak, is down here in the green, and our output, our load voltage, is in the maroon. So the first thing you'll notice, besides the fact that it's a lot larger, which we would expect, is that it's asymmetrical. Right? This is not a nice pure sine wave. If you look at it quick, you might think so, but a second scan, a second look at this will show, no, this is definitely not a nice pure sine wave. A couple of things are noticeable. Right, here's 0. This positive peak doesn't even make it up to 2 volts. The negative peak, on the other hand, is going beyond negative 2 volts. And it's not just because there's a DC offset. Right? When you look at this negative peak is rather sharp compared to this broad positive peak. Right? So sharp negative peak, broad positive peak. This does not exhibit what we call half-wave symmetry. If I were to take this negative peak and flip it up to here, right? Flip it around the 0 axis, kind of like you would do with a full wave rectifier, right? If you flip this up, you're going to get something that peaks up like this, all right? And if you were to take that waveform and slide it over so that it sits on top of this piece, the positive half wave, you would notice that they're not the same, right? It's not just a simple matter of scaling. The actual shape of this thing is different. If they happen to be identical, if the two pieces are identical, the wave has what we call half-wave symmetry. So this wave does not have half-wave symmetry. Why is that important? Well, any deviation that you get from a sine wave is, by definition, a form of distortion. So what I want when I throw a sine wave in is I want a sine wave out. Nothing more, nothing less. Right? I just want the sine wave to be bigger because it's an amplifier, but that's it. I don't want to change the shape of the waveform. This is a very important point. I cannot stress this enough. If you change the shape of something in the time domain, right? If you start off with a sine wave and you bend this like we have here so that the positive and negative peaks don't look the same, you sort of squish the waveform here and you elongate it over here. Whatever you do, I don't care how you change this thing, right? If you put a big bump in here or a squiggle over here, whatever the heck it is, if you change it in the time domain, that means you have changed it in the frequency domain. And since we started off with a simple sine wave, which is the basic building block, you don't get anything simpler than sine wave, that means we've added frequency components. It's that simple. You change the shape, you've added frequency components. Now those frequency components, because this is just simple single source kind of input, right? Single sine wave input. It's what we call harmonic distortion, because these new frequencies are going to appear at harmonics of the base frequency, the original frequency. And by a harmonic, what we mean is an integer multiple of that frequency. So we started off with 1 kilohertz. So what I'm saying is this new waveform must have some 2 kilohertz, 3 kilohertz, 4 kilohertz, 5 kilohertz, whatever it takes to make up this waveform, right? So it's just integer multiples of the original frequency at the appropriate amplitude and the appropriate phase. When we add them up, we get the new wave shape, right? So you can decompose any non-simple sine wave into a whole bunch of sine waves, right? That's basic Fourier analysis. You take a non-sinusoidal waveform, I don't care what it is, square wave, triangle wave, a ramp function, or sort of squished, manipulated kind of sine wave here, whatever it is, you can decompose that into a whole bunch of sine waves. So you start with the fundamental, which is the original sine wave, and then we add on all of these integer multiples, these harmonics, at the appropriate amplitude and phase. If we do it right, we get the appropriate amplitude shape out of the resulting signal. Okay? We don't really care how that happens right now. We just know that it does happen. Now, if you have something that does not have half-wave symmetry, right? This wave does not have half-wave symmetry. What that means is there must be at least one, probably more, but at least one even harmonic. If it has half-wave symmetry, that means there's no even harmonics. So if I'm starting at 2 kilohertz, if I'm starting at 1 kilohertz, the even harmonics would be 2 times, 4 times, 6 times, 8 times. In other words, 2 kilohertz, 4 kilohertz, 6 kilohertz, 8 kilohertz, so on and so forth. So if we had half-wave symmetry, that means all of the distortion products that we're talking about would be at the odd multiples, 3 kilohertz, 5 kilohertz, 7 kilohertz. Because this does not have half-wave symmetry, there's got to be at least one even in here. There's got to be at least, a 2K or a 4K or a 6K. I don't know where it is. Probably there's going to be more than that. There's maybe a little bit of 2K and some 4K and so on and so forth, along with odd harmonics as well. All right. So the first thing is I want to figure out what the THD is, the total harmonic distortion. So we represent that as a percentage, right? You'll say the THD is, let's say, 1%. What does that mean? That means this waveform, if we were to say this was 1%, it's 99% pure sine wave that we started with, and then 1% of this is these extra harmonics, these extra frequencies, right? All summed together, the lump of them work out to 1% of the total. All right. Now, in the old days, when we would make distortion analyzers, we would literally, at the output of the amplifier, put in a very, very sharp comb filter, a very sharp notch filter that would get rid of the original sine wave that you started with. And all you would be left with would be the harmonics. We would then take that signal, right, that harmonic signal, harmonic rich signal, and we would just put it into a true RMS reading sine wave voltmeter, and whatever that comes up to, we would then compare it against what the original signal was, and we would derive a percentage from it. Nowadays, we have mathematical techniques that we can do. So the waveform is actually digitized internally, right, in Tina TI here, and then we do a mathematical decomposition on it, a Fourier analysis on it, to find out what these pieces are, right? So Tina TI has this built in for you, but it doesn't just do THD. It does more than simple THD. So how do you get it, right? I want to know how bad this is. The first thing I'm going to say, by the way, is if you can see it, if you can look at the waveform, right, and you can see, like here, there's an obvious asymmetry in the wave, whether it's to the positive or negative, or even side to side, what we call quarter wave symmetry, right? If I split this down here, is this half like this half, or is this half like this half, right? That's quarter wave symmetry. If you can see that there's a difference, you pretty much have over 1% total THD. If you can't see it with the naked eye, that doesn't mean that you don't have distortion. It's just not easy for your eye to discern, let's say, 0.2% THD in a sine wave. But we have machines that can do it for us, right? So what we do in Tina is we come over under the analysis, and if you come down through here, almost to the bottom, it says Fourier analysis. So you select this, and there's a bunch of settings here, and for the most part, you can leave these where they are. The only thing you really need to sort of fiddle with is if you have multiple output points, you would have to select from this drop-down which node you're interested in. In this case, I only have the V load, so that's what it's going to default to. So calculate. Boom. I'm going to pull this down so you can see this. Now we've selected 16 harmonics. This is going to compute the values for the first 16 harmonics. And I get a columnar output here, a table value. The first one is the amplitude. The second one is the phase. And we just go up by number, 0, 1, 2, 3, 4, in terms of where they are in the list. All right. So I have the amplitudes here, and then I have the phases. So 1, right, K is 1. That's our base frequency. 0 is a DC offset. And then we just have the multiplies. So we started off with 1 kilohertz. So this is the 1K. This is 2K, 3K, 4K, 5K, and so on and so forth. So I can see my base input signal that is just about 2.1 volts worth of original 1 kilohertz sine wave. But then I've got nearly 200 millivolts, right? 197.6 just about millivolts worth of second harmonic. And then a little under a millivolt of third harmonic, and just about 1.9 millivolts of fourth harmonic, and so on and so forth. And when these are all added up, right down here, it tells you that's 9.4622%. That's your THD. That's your total harmonic distortion. Okay? That's kind of high. If you're talking about a hi-fi amplifier, this isn't. We don't really start talking about hi-fi quality until we get well below 1%. I wouldn't call 0.5% THD hi-fi, right? So 9.4, not so good. Now that might be perfectly fine for, an intercom or something like that. You don't really care about super high fidelity, right? Certainly, there are circuits we build that have much, much more harmonic distortion. A guitar fuzz pedal has tons of distortion. You put that in there on purpose, right? That's the whole point of the thing, is to create tons and tons of distortion. You create all these new harmonics. And, fuzz, guitar fuzz, sounds very bright. Why? Because of all of these harmonics that are so much higher in frequency, in other words, higher in pitch, than the original frequency you threw in there. Okay? All right, so you can get an idea of what's going on here. But what's really interesting is you can draw this. You can actually see the spectrum. So just click on draw, and you get this output. The top is the amplitudes of the various harmonics, and the bottom are the phase shifts. Okay? Now, this defaults into a linear axis over here, and this will obscure the smaller harmonics, right? This only shows a little bit of the DC offset. Here's the 1 kilohertz base frequency that we threw in, and we can see a little bit of the next harmonic, right, at 2 kilohertz. But you can click on here, right? Click on the vertical axis, and then come down and hit your properties. You can put this in a couple different forms. So that scale, instead of being linear, make it logarithmic. So this will cram in those smaller things. You'll be able to see a lot better. All right? So you can see this is going by factors of 10, right? 1 milli, 10 milli, 100 milli, 1. And now you can see some of these smaller ones. Of course, in this case, it's maybe not good enough, but we can change the bounds on here. So instead of having that be 1 mil at the bottom, let's make that 0.1 mil. And lo and behold, you can see those higher harmonics, and they are quite low. All right, they are quite low. So that second harmonic is really a biggie. The fourth harmonic is pretty big. We're getting some out of the third harmonic. The lack of symmetry that I was talking about indicated that there were going to be some even harmonics. Clearly, we can see this is the case, right? 2 and 4, 2 kilohertz and 4 kilohertz, very strong here. So that lends credence to that whole idea. You might also, instead of doing it that way, you might also want to do this with a decibel layout that sometimes works a little nicer. All right? So you can see it in terms of decibels, but it's the same basic shape when you do the log, because really dB are logarithmic, so there you go, right? And now you can see what's what. So here's the thing to remember, and that is you can have two amplifiers that have the same THD, right? Amplifier A, let's just say it's 2%. Amplifier B, also 2%. That doesn't mean the distortion is the same, because the first amplifier could have, like this, a very strong harmonic here at 2 kilohertz, pretty strong one at 4, and all these other ones are pretty weak. The other amplifier, which is also coming up with the same total harmonic distortion, could have nothing here at 2 kilohertz and a huge value at 3 kilohertz and maybe 5 kilohertz. But when you add up all these extra pieces, it's going to add up to the same total percentage, right? So THD is kind of a gross measurement in terms of the distortion of the amplifier. It would not be true that if I had two amplifiers that both measured the same, like in this case, nearly 10% THD, they're going to sound the same because the distribution of these harmonics could very well be different. All right? Okay. So takeaways from this. First thing is, if you're throwing in a sine wave and you get something other than that nice, pure, pristine sine wave out, you've somehow changed the shape of the waveform in the time domain, then we have added frequency components. We've added harmonics to this. Each one of those things should not be there. We should only have the original signal. And if we sum up all of these extras, we compare it to the original signal, bingo, that's your total harmonic distortion, right? So any warping of that shape indicates there's extra frequency components, right? So any non-sinusoid, this is the other way to say it, any non-sinusoid can be decomposed into a whole bunch of individual frequencies. Okay, you got your fundamental and all these other added things. Okay, beautiful. So now we know how to do distortion measurements in TINA. That's fairly useful, right? So when you're talking about just using your eye, yeah, you can tell someone's got 5 or 10% THD. But if you're talking about, 0.05 versus 0.1%, not so much. You're going to need to do a proper analysis, right? So remember, just go through the Fourier and you can see the total. And then if you really want to break it out, you can use the draw option on there. All right? Great. Beauty. Any questions? Put them in the comments. We'll see you next time. Have a good one.